Okay, so we've got an exam on Thursday. 48 hours from now, you'll be starting your first test, and it covers Chapter 2 and Chapter 3. And so that's from the beginning of the semester up to and including the material in today's class meeting. And there will be problem-solving questions on there, but there won't be any short answer or conceptual type questions. It's just problem-solving for this one. I'm providing an equation sheet, so you don't need to prepare any kind of a formula sheet to bring with you. Everything you need is already on that formula sheet that I'm providing. It'll be Dr. Michelson who's administering the test to you because I'll be out at Cabell Midland High School trying to recruit new students. So I'll be there while you're suffering here. All right. So any questions about the exam? All right, so today we're going to talk about buoyancy. I know you've got some hands-on experience with buoyancy last week in the lab. And in fact, in today's lab, we're going to continue talking about some things that are related to buoyancy and also related to stability of floating bodies, which we're going to talk about in today's lecture. To be honest with you, I forget where we're at as far as the 2 o'clock versus 3 o'clock thing. Maybe you remember. The first part of the alphabet. Last time we had an in-person lab, which I guess that would have been the week we did the computer stuff, right? So that was the week that we did EPA net. The first part of the alphabet, was that at 2 o'clock or was that at 3?
3 today, the first part of the alphabet.
All right, so A through K or whatever it is at 3 today. Second half of the alphabet at 2. Thanks, Josie. All right. Now, I just wanted to quickly touch on some interpretation of geometry because, this could conceivably come up in the exam. Oh, by the way, I'm glad I thought of this. Student Affairs said we had a COVID case in the class. Since we all wear masks during class, nobody in here needs to quarantine. They encourage you to get tested if you want to be sure. They do the free walk-in testing over at the Student Center, and if you have any symptoms, also be testing. But since we wear masks, nobody needs to quarantine. Be sure that the mask is up over your nose. So the mask needs to be up over your nose. All right, great. So geometry interpretation. When you have a front view, and this side view doesn't necessarily give you everything you need to know in order to determine the dimensions of this triangle. Let's say that you had a problem where you needed to find the hydrostatic forces on a triangular gate, just hypothetically. So you've got the front view, which tells you the projected height, but that projected height of 110 centimeters isn't the same thing as its physical length. So its physical length from the top to the bottom, you can calculate, but it's not immediately given to us. And so let me just put something up here on the whiteboard to illustrate. We've got the physical inclined triangular gate, and its vertical projection is 110 centimeters, and then the projection of its width, this dimension along the bottom is 200 centimeters. I guess obviously this isn't to scale because I drew one line longer than the other, but I think what you can see is that you would find the actual physical length of that triangle from the top to the bottom by taking the square root of the sum of the squares. So 110 centimeters squared plus 200 centimeters squared, and take the square root of that. So L, the physical length of that, would be 228.25 centimeters. All right. Now, don't take this as any specific hint of what you definitely will see on the exam Thursday, but just my past experience has told me that sometimes it's a sticking point interpreting the visual geometry of the gate. And so I wanted to remind you that in a front view, that doesn't necessarily give you the physical length. It's the projected distance from the top edge to the bottom. All right, so I see some nodding heads there. I think message received. Any questions before we move on from this one? All right, so where we left off is a discussion of buoyancy. And remember, the ways that we can calculate buoyancy is you can either determine the forces that are pushing up from beneath minus the forces from above that are pushing down. And so it's the net difference between the pressure forces on the bottom of an object versus the ones that are on the top. So that's one approach to finding out the buoyant force. The other is just to look at the volume of water that's displaced by a submerged object. And so here, this object is fully submerged. So what I'd like you to do is address this question of, will it float or will it sink? So what we know is the dimensions of the barrel. The barrel is 2 meters long, 2 meters in diameter and 180 centimeters long. So 180 is the distance from this edge to the other, and then 2 meter diameter. So first thing you need to do is calculate the volume of water displaced. And it's fully submerged under the water surface, so the volume of the barrel is the same thing as the volume displaced. And it tells us it's water, so we know that the unit weight is 9810 in that case. Now here we have this dimension of 5 meters. Let me ask you this, a conceptual question before I turn you loose on your calculators. Does the buoyant force change based on how deeply submerged an object is? No, you're right. You're right. Why not? Why doesn't the buoyant force change based on how deep it is?
It's only based off of the volume.
Volume and unit weight. And so neither of these things change based on depth. The unit weight is constant. You know, liquids are only minusculely compressible. And you'll only notice a difference in the unit weight of the liquid when you go thousands and thousands of meters down. That's when it's such a big pressure that maybe the fluid's compressed a little bit. But basically, density of a fluid is constant, of a liquid is constant. And so will the unit weight. And the volume isn't going to change. I mean, unless it's like collapsing as you go deeper under the ocean. And then the buoyancy would change. But let's say this isn't collapsing. So sometimes you're going to be given useless information. When you graduate and go on to your professional career, most of the information people give you will be useless. Your clients will give you useless information. Your boss will give you useless information. Definitely your spouse and your children will give you useless information. But basically, you just need to get the habit of filtering out what's not important and focusing on what is. So here, calculate the buoyant force, and then I tell you the mass of the barrel. So determine if it's going to float to the surface or if it's going to sink. So right now it's not in equilibrium. It's been released, and we're wondering, is it going to float to the surface or is it going to sink? And the way that you can know is by comparing the buoyant force to the weight. All right, so let me pause the recording for a second, give you some time to calculate the magnitude of the buoyant force, and then compare it to the weight. I'm glad that my plan to trick some of you worked. Given these weird units here, 180 centimeters, I mean, it would have been more normal for me to say 1.8 meters, right? But, I mean, you get data in all sorts of forms. So, I mean, I noticed several people who said that was 0.18 meters rather than 1.8. So and that's what I'm aiming for, is to get you, like, accustomed to totally questioning all of the data that you see. All right, so the volume is just the area times the length. So here's the area, 3.14 meters squared. You multiply by the length of the barrel, and that gives us that the volume is 5.655 cubic meters. It's all beneath the water surface, and so that's how much is displaced. And the buoyant force is 55.474 kilonewtons. And then whether it'll sink or float, we have to compare it to the weight. And so we know the mass, and weight is mass times gravity. So we've got 55 kilonewtons pressing up, but only 15.7 kilonewtons going down. So it's going to move towards the surface until it comes into equilibrium. And what it'll do is it'll float until only enough of it is submerged so that the buoyant force is equal to 15,696 newtons. So that's what will dictate how much it floats up out of the water. And so it looks like less than half of it will be submerged, because when all of it is submerged, we get 55,000 newtons of buoyant force, and we only need 15,000 newtons of buoyant force. And so you could calculate what percentage of the barrel will be below the waterline just by determining the ratio of the weight to the potential buoyant force. And then that'll tell you the percent submergence. Another way to look at it, just if it's going to float versus if it's going to sink, is you can calculate the unit weight of a solid object. And the unit weight of the barrel would be its weight divided by its volume. And so since the unit weight of the barrel is less than since the unit weight of the water is greater than the unit weight of the barrel, then it'll float. Yeah, because it's less dense, has a lower unit weight, so that object will float in that liquid. All right, so that's buoyancy. Do you have a homework problem that includes a drawing like this? No? Oh, maybe you're missing out. I need to put that one back in the rotation. It's such a great problem. All right, let's talk about something else. Let's talk about, related to buoyancy, but we're going to talk about stability of floating bodies. This looks like a real fun time, sitting on the edge of a boat. They've got their shoes on, sunblock, everything. Now, why do you suppose they're sitting on that edge of the boat? Well, I guess it's so it, to help it sit more upright in the wind. The boat, it's not like if they moved off that ledge, the boat would sink. I don't think it's like an emergency thing. But by moving their weight onto that edge, it brings the sail more up in the wind. And when the sail is more up in the wind, they're able to get more forward thrust. Another interesting thing about this picture is you can see beneath the waterline just a little bit of a shadow here, that there is a heavy piece of metal, part of the ballast, that goes deep under the water that's not quite pictured there to help maintain the stability of this floating body. So what we're going to talk about today is some calculations that can help us to determine whether a body that's floating on the surface of the water is stable and will naturally right itself when it gets pummeled by waves and wind, or whether that floating body is prone to tipping over and is unstable. And so compare these two cylinders. You've got a submarine on the left where it's stable, there's people standing on the top. The cylinder on the right, you can see the boy is struggling to maintain his balance. There's some grip tape on there. It's probably a game of some sort. But why is it that this, there's no grip tape on the top and they're not struggling to maintain their balance? There's something about that submarine, and it's not just its size. There's something else about it that makes it naturally stable so that this tower always is upright compared to the log, where the log isn't naturally stable. So that's what we're going to address today, is how you design something to be naturally stable. Now, let's consider this case. We've got some sort of a submerged body that if we let go of it, it could float to the surface. And so it's either like under the water surface or up at the top. It would have the same effect as far as stability. But what's important here is we're looking at a cross section. That log that the boy was on, what if they put a bunch of lead weights at the bottom of the log? So that's what this is. They've affixed a heavy weight at the bottom of it, and that keeps it a lot more stable because it's naturally going to have that heaviest part at the bottom, and so it's less prone to tipping. I think instinctively you kind of already know that. There's a couple of points that are labeled here. C, the center of buoyancy, the location of that is determined just by the shape of the object. So it has to do with the water that's been displaced. And so where is the center of buoyancy has no effect based on the weight being there. The center of buoyancy is just dictated by the shape of the object and the water that's been displaced. But G is the center of gravity. And what you'll notice is that the center of gravity is lower than the middle point on this circular cross-section. And the reason why it's lower than the middle point is that we've added this weight to the bottom. And so G is kind of like a weighted average of the location of the center of gravity. And what brought it down away from the center of the circular cross-section is that we have a little extra weight at the bottom. So does everybody feel okay with why C and G are in those respective locations? Does that make sense to everybody so far? All right. Now think about what if, all right, we've defined these terms. What if you twisted this stable body? So if you rotate it, it's going to right itself naturally. The C will stay in the same location if you rotate it. It's not moving. But if you rotate it, G, let's say if you turned it counterclockwise, G would move up and to the right. And that's what's depicted here in image C. So if you rotate it, what that's going to do is it's going to naturally right itself because G is acting downward. That's the center of gravity. The center of buoyancy is acting upward. And think about what if you put your finger on the page. And so you put your finger on C and another finger on G, and now push up on the circle at C and push down on the circle at G. Think about if you've got a piece of paper and you push up and down on different locations, it rotates. And so the buoyant force is pushing up in the middle. The gravity force is going down on the right, and that causes it to rotate. And when is it going to stop rotating? Like it's going to rotate here at C. Is it going to just keep rotating forever? No, it'll stop eventually. When will it stop rotating?
Whenever A has been achieved again.
Whenever A has been achieved. That's right. So when this is going to rotate until G is beneath C, because I'm pushing up on C and down with G, so it's not going to have any more tendency to rotate once it gets back over here to this first case. So this is stable. B is just neutral. You know, if you rotate it, it will move, and then it's not going to move back. But object C and A is an example of something that's stable, and when you twist it out of its initial equilibrium, there exists a righting couple. A righting couple just means it's going to right itself. It's going to go back into the original position. So if we wanted to describe a rule, like if there was some sort of an if-then relationship, what we could say is if G is below C, then the object will be stable. Okay, so that's kind of one rule. If the center of gravity is below the center of buoyancy, then it will be stable. So that is true. But what I didn't say is only if. Because there are other cases where you can have stability. So this is just one situation where stability can be achieved, but there are others as well. And so I'm going to tell you about that other case where there's also stability. But this is the simplest case. It'll definitely be stable if the center of gravity is below the center of buoyancy. Okay. Has anybody actually seen one of these big shipping container carriers in person before? Maybe you were on a cruise or at a port. These ships are incredible. I mean, if you just stand next to a container, it's large. I mean, think about if you can walk into these shipping containers. I don't know exactly what their height is. I think it's maybe 10 feet. But they're big, like if you've ever stood next to a shipping container. and look at how many of these they've got stacked. Doesn't it seem like that boat would tip over? Like it just seems top heavy when you first look at it. So there must be something about these ships that makes it so they're not actually top heavy. You know, like if it genuinely was top heavy, then you get into a big storm and it's just going to dump all those containers into the ocean. And you don't hear about that happening. I mean, occasionally it does, but not very often. We're going to talk about what is it about ships that allows you to have so much mass so high. It's because of the shape of the bow. That's right. Now, in a case like this, our earlier rule doesn't apply. In this case, the center of mass is above the center of buoyancy. So there must be something else to it. And that's what we're going to talk about. Okay, so this ship, just as an illustration, C, remember, is the center of buoyancy. And the center of buoyancy, its location is determined by the shape of what's below the water surface. And so it's basically you're looking for the average location for what's below the surface. And so C is kind of like the area weighted average location for what's below the water surface. G is determined by what's in the ship, not by what's the shape below the water surface, but like if we kept stacking more and more weight up high on the boat, then that would elevate G further and further up. Now, if the ship tips over, then the center of buoyancy is going to change its location. Now let's assume that all of the cargo is strapped down. So when the ship tips over, the center of gravity is not going to change as long as everything is secured. But when the ship tips over, the center of buoyancy is going to change. So here's the ship tipped over. Now look, initially what was beneath the water level was AD. So this line AD is what used to originally be the line, the water line. But when the ship tips over, because of the shape of that bow, now you have more area on the right side of the boat, more submerged area. So this triangle OBA, that area is now over on the right-hand side of the ship. And so there's now more submerged area on the side of the ship that's starting to tip over. And so now look at the righting couple. That's a phrase that we saw in the previous slide, righting couple. R-I-G-H-T-I-N-G. It's the couple. A couple means one force is one direction and another force is the opposite direction. And righting means it's going to set it right back up into its original stable position. So G is down, the center of gravity. So gravity and all the mass of the ship is acting downward. The buoyant force is acting upward. And so we've got this couple that the forces are trying to stabilize the boat again. So C is pushing up, G is down. So it's the same thing. If you push down with one finger, up with the other, it's going to twist the boat back into stability. Now, M is something that we haven't talked about yet. M is this, it's an imaginary point. It's not imaginary, but it's not like an actual thing that's painted onto the boat. It's just the location that if you have a center of gravity, the center of buoyancy points up through the metacenter. And so if we tipped it over even more, so if this boat tipped over even more dramatically, C would shift even further to the right. But C would point towards the metacenter. It's kind of the axis of rotation through which the ship is tipping. So like if we tip the boat back and forth, M would be, the metacenter is the point at which it's rotating about. It doesn't rotate about G, the center of gravity, but C, the buoyant force is pushing up towards the metacenter. And so there's a new rule of whether or not the ship will turn over or not. And so the first one was if the center of gravity is below C, but if the metacenter M is above G, the center of gravity, then it's also stable. So that's the second of our two things that are indicators of stability. So let's write that on the board as well. If M is above G, then stable. So M, the metacenter, is just the location that C is pointing towards in all cases. The center of buoyancy always points towards the metacenter. If G is above M, then the ship will tip over. It's not stable. Now, to calculate the location of M, we have to take the area moment of inertia into account. And that's something that we've already addressed in one other context this semester. But the area moment of inertia for stability of floating bodies type problems, let's take this rectangular barge as an illustration. So this barge, it looks like it's maybe carrying big blocks of rubble. Maybe they're reinforcing a breakwater or something. But the longer dimension is A, and the shorter dimension is B. So here's the width of the barge and the length of the barge, and whichever of the two is shorter is the term that is cubed when you're doing area moment of inertia calculations. And so this is not the area moment of inertia looking at from a side view, it's the shape of the barge from a top view. So think about what would make this barge unstable. It was really narrow. So B, the wider B is, the more likely it is to be stable. And think about, have you ever seen those Hawaiian canoes? When I say a Hawaiian canoe, do you know what I mean? What do I mean by Hawaiian canoe? It's got like the big thing on the side, right? Like so that they can play around in the waves. They've got it's called an outrigger canoe. I should include a picture of that in my notes. Now that I've brought it up, I have to show you a picture. It's always dangerous when you Google search something, but I bet this will be all right. Yeah, all right. So a Hawaiian canoe it's got this thing on the side here, because if it was really narrow, then it would just tip over too easily. By making it more wide, it becomes more stable. That's why Hawaiian canoes have this thing on the side, is because they're meant to be ocean going. You know, they're going to be in lots of waves. We're not talking about just a little river or something. So the width term, what lends towards more stability is a wider barge. Okay, so here's the formula for calculating the distance between M and G. So GM is called metacentric height, and it's a distance term that has units of length, whether it be meters or feet or whatever. So what you do is you calculate the area moment of inertia defined by the water line. So that's this area moment of inertia, like a top view area moment of inertia. So I divided by V, which is the submerged volume, that's the first term, and the bigger this is, the more stable it's going to be. So if you have a big area of a moment of inertia and a low submerged volume, that's going to mean it's very stable. But the larger the submerged volume is, if you have it really deep under the water, then that's going to make it less stable compared to something that has a shallow draft. The other term here is CG, so the distance CG, and that's how far above the center of buoyancy the center of gravity is, because there's a limit. Remember what we talked about when we were looking at it just from this perspective is if we kept loading stuff higher and higher on this boat, like really heavy stuff up high, it's going to tip over more. So if you put heavy stuff up high, it's going to be moving G higher and higher and higher. So there's a limit to where G is allowed to be. And the rule is that if G is above M, then it's unstable. That's too high. But as long as G is below M, then it's stable. And that's what this method allows us to do, is it allows us to calculate how far above G the metacenter is. And if G goes above it, so in other words, if this is negative, then your boat's going to have a real negative day. You know, it's going to tip over. It's unstable if GM is negative. But if it's positive, meaning that the first term is larger than the distance between the center of buoyancy and the center of gravity, then the body is stable. Okay, so to practice these ideas, I've got an example conceived for you of a barge that is 6 meters wide, 15.25 meters long. So we're looking at a front cross-sectional view of it. So that's the distance into the page. And it's loaded with rocks. So the center of mass is at G. I haven't yet told you where is the center of buoyancy. The center of buoyancy is just halfway down the submerged location. So this barge overall is 2.44 meters in height. And based on how much load it has, that is how you're going to calculate D. Let me hand this out because I've got a piece of paper for you. I'd like you to scoot next to another student and work through this with them. Here you go. Okay, so I take you through this step by step, like A through H. The order of it is implying basically all of the things you need to know to assess stability. So first of all, calculate the weight based on the mass. Calculate the buoyant force when the system is equilibrium. Well, that's not actually a calculation. That's more of a concept question in part B. So nobody should be sitting alone for this. You need to scoot next to another student and work this in pairs, all right? One thing I think is helpful to visualize this problem is draw the center of buoyancy on the page. Like put a little dot to indicate C. And I think when you do that, you'll immediately see that, you know, it's halfway down from the water line to the bottom. So D divided by 2 is the distance from the water line down to C. But then to calculate from C up to G, you also have to know how far is it from the water line to the top edge of the barge. So we have the overall distance, 2.44, and if you subtract out D, then that'll give you from the water surface up to G. So it's kind of a two-step thing in order to calculate the distance between the center of buoyancy and the center of gravity. All right, so let me go through these calculations and see if you're on the same page with it. Okay, to find the weight of the system, we just multiply the mass by G. So 1.7 million newtons. And when the system is in equilibrium, by definition, that means that the buoyant force is equal to the weight. So it's sitting in the water here at this depth D. It's in equilibrium. So when it's in equilibrium, the buoyant force and the weight are equal. And then I use that to calculate D. So how deeply it sits is going to be dictated by how heavy it all is. And so it's going to come into equilibrium based on how heavily laden it is. And so from that we can see that the buoyant force is the unit weight multiplied by the volume displaced. And all the other terms are known except for the depth of submergence. We know the width of the barge is 6 meters, the length of the barge 15.25, so the only term that is unknown is the depth of the barge. So we solve for D and get that it's 1.978 meters. I circulated around and seemed like most people got that same thing. So that's D. Any questions so far? Okay, next I suggested that you draw a sketch of the barge from the top view, simply because, if you sketch out what its top view looks like, then it's going to be easier to identify the shape of it and the dimensions. And so here's my sketch, 6 meters wide, 15.25 meters in length, and then in part E, when I'm calculating the area moment of inertia, I can see I'll just cube the smaller of those two dimensions. So, like what makes it the width versus the length is simply which is the lesser of the dimensions. So 6 meters is the width because it's the lesser of them. So that's the one I cube. That's kind of the point of vulnerability for stability. It's more prone to tip over side to side than front to back. I once spent a summer on a boat out in the Atlantic Ocean, and it was 100 feet long and probably about 15 feet wide. And these waves that would hit us, we would rock side to side about 45 degrees, and then front to back we'd only do about 10 to 15 degrees because it was longer than it was wide. So the side to side rocking was a lot worse. Man, it was awful. All right, so F, what is the distance CG? All right, so CG, by definition, C is from the waterline halfway down, and then from the waterline up to G is simply going to be the 2.44 minus D. So that's what I do here. I've got a little sketch of it where you can see that the 0.989 meters, let me zoom in on that sketch. All right, so it's 1.978 from the bottom edge to the water surface, and so the distance with this little arrow from the water line to C is going to be half of that. And then there's 0.462 meters from the water line up to C. So overall, we add the two things together, and CG is 1.451 meters. So that's the physical distance between the center of gravity and the center of buoyancy. And then GM is basically asking how far above the center of gravity is the metacenter. And so since it's positive, it's going to be stable. That means we could load this barge even a little bit more because, it still can sit deeper in the water. It's not going to submerge itself yet. And if we load it a little more, that's going to bring the center of gravity even higher, but we've still got a little bit of leeway. We got about 6 centimeters of leeway. But then if you load it even a little bit more than that, then it would become unstable and prone to tipping over. At which point we could put one of those Hawaiian outriggers on the side, and then that would make it wider, and then it would be stable again, right? So those are things that you can do to adjust the stability. So in the lab today, we're going to be playing around with that little boat from last week, and we're going to cause it to tip over. We're going to measure the angle that it's tipping over and how high we take the mass up. And so it's going to be kind of like a physical experimentation having to do with stability of floating bodies in the lab today. Any questions about this example? Yeah.
What happens when GM equals 0?
When GM equals 0, I don't know. I guess that's kind of a no man's land, Like it'll be stable until a wave hits it, and then it'll tip over. I'd say if it's 0, that's unstable. The fact is, the bigger GM is, the more resilient your boat's going to be, because if this gets tipped over due to a wave or some wind or something, how much it can tip over and then recover is in part dictated by how big GM is. And so right now GM is pretty small, so I guess we could just say it's going to not be able to recover from much of a tip. I had one other note to myself on this example. Oh, I remember, it's in the slides here. If the depth of submergence exceeded the physical height of the barge, it would sink. And I guess maybe that goes without saying, that if we put so much stuff in here that D required is bigger than 2.44 meters, then it's unstable if it's at the bottom of the ocean. That's another definition of unstable, if it's overloaded. All right. All right, just one more example for us to look at. And this is going back a bit to hydrostatic forces. So hydrostatic forces on a curved gate. And this is an unusual system, and I wanted to talk you through this and then for us to do some calculations together. So let's start over here where we know something. We know atmospheric pressure is 0 gauge. All right, so the pressure of the water is the same as the atmospheric pressure right here at the boundary between the two of them. So water pressure is 0. What happens to water pressure as we go down through a fluid? Increases. Okay, so if I go down a little bit, the pressure increased, and then I go sideways, nothing happens to the pressure when I go sideways. Okay, and I go back up again. All right, so I'm at this point. You can see where my cursor is. What's the pressure in the liquid right here at this depth? I'm at the same elevation as the water line over on the right. So what's the pressure there? What was the pressure here? 0. What's the pressure over here? 0. Right. So same elevation, same pressure. So I'm at 0 pressure here, where my cursor is. What happens if I go above that point? Now, just by the way, let me draw this in there, just so it's even more obvious. I'll draw this little dashed line over to here. All right, just to help us keep track of where the pressure is 0. It's really important that this be dashed. There we go. All right. All right, 0 pressure here. So everybody understands why, because it's at the same elevation as over here on the right. Okay, so then when we go up, what happens to pressure as we go up through a fluid? It decreases. So the pressure is negative in gauge terms. Now, it's not negative in absolute terms, not necessarily, but it's negative in gauge terms. And so it's suction. So the higher we get in this fluid, the pressure is becoming more and more negative. So what happens is the water is actually sucking this gate down and to the right. You know, rather than pushing up and to the left on the gate, like that would be the case if it was beneath the water line. But this gate is above the water line. So the water pressure is pulling down and to the right. Okay, so let's go just as a practice measure, go ahead and calculate the horizontal and vertical forces that act on this gate. And let's not worry about the location of the forces. Let's just find the magnitude of each. What's the magnitude of the horizontal force? And remember that the horizontal forces on a curved gate, you determine those by envisioning the vertical projection. And so here we have a curved gate, and it says that the gate is 2 feet wide. So that means into the page it's 2 feet. Let me erase the whiteboard here. And let's draw the shape of the vertical projection. Okay, so this curved gate has 2 feet of width. And then that 3-foot radius tells us that the vertical projection of the curved gate has a height of 3 feet. Okay, so the vertical projection is a vertically oriented rectangular gate with the width of 2 feet and a height of 3 feet. Okay, so to find the horizontal forces, just find the force on the centroid. So we got to ask ourselves, like, what's the relationship between where's the water line to the centroid? So, like, what's that distance? Remember, force hydrostatic is the pressure at the centroid times the area, which is delta H times gamma times the area. Okay, so the gamma here, it says it's water. So unit weight is 9810 newtons per meter cubed. Area we've defined by the vertical projection. I don't want to say too much more. I want to pause for a moment and give you a moment to think about what's delta H, and then calculate the hydrostatic force, and then what's the concept for finding the vertical force. Whenever we've had these curved gates, how did we find out the vertical force component?
The weight of the water.
Weight of the water. And until now, when the gates were below the water line, it was the weight of the water above the gate. So it's been the weight of the water from the water line to the gate. What do you suppose the rule would be if the gate is now above the water rather than being below it? What weight should we calculate? I know somebody's got a guess. Guesses are low stakes. No humiliation if you're wrong when you've got permission to guess. So what weight of the water are we going to have to deal with here? Because we want to find out vertical force. How much is the water sucking that gate downward? So what's going to be the weight of the water that we talked about?
Weight of the water above the water line.
Good. So it's from the water line to the gate. So it's just how much water is there from this line projected over sideways up to the gate. So you're going to do that same thing where you think about in 3 dimensions, what do the elements of the water look like? Like, what are the shapes? You know, you've got a wedge-shaped component, you've got a rectangular box. How much water is there? What's its volume and what its weight? And that's how you find the vertical forces. All right, so I'm going to pause for a second and allow you to reason through both these horizontal and vertical forces. Okay, here's a little sketch of the system, and I've also written it on the whiteboard that the delta H is 2.5 feet above the liquid level. So we have to go from, I'm not calling it the water line since this isn't water as we've just talked about. So from this liquid up to the center of area of the projection. So our vertical projection has a centroid at the middle of the 3-foot height. So it's 1.5 from this edge up to the centroid, and then 1 foot down from this edge to the projected liquid level. So that is why the delta H is 2.5 feet. The unit weight here in traditional units, 50 pounds of force per cubic foot. And then we multiply that by the 6-foot cross-sectional area of the projection. So 750 pounds of force. Now the minus sign here just means that the force is to the right. So the water isn't pushing against the gate, but rather, it's not water. The liquid pressure isn't pushing against the gate, but rather it's sucking the gate inward towards the liquid. And then the vertical forces, you can see I've broken it up into a wedge-shaped element and then a rectangular-shaped element. And so the volume of the wedge here, so it's a quarter circle multiplied by some thickness. So a quarter circle gives us a cross-sectional area, pi r squared divided by 4, gives us the area, and then if you multiply that by the width, And the problem statement says here it's 2 feet wide. So the area multiplied by the width of that element, that has a volume of 14.137 feet, and then the box-shaped element beneath it has a volume of 1 by 3 by 2. So that's 6 cubic feet. And the overall weight of the water from the liquid level up to the gate is 1,006.7 pounds of force. So we multiplied the cumulative volume by the unit weight. And so that force is down. So if we wanted to hold the gate steady, like if we were supporting the gate at its edges, you'd have to push up on the gate vertically to hold it steady based on the suction it's going to experience downward. And you'd have to push on the gate to the left to overcome the forces that are pulling it to the right because of the suction it's experiencing. So it's just an unusual case that occurs when the gate is above the liquid level and is experiencing a suction negative pressure. All right. So 48 hours from now, you'll be finishing the first exam. Be feeling really good about how well it went because you were prepared, didn't cram the night before, got plenty of sleep, feel relaxed and happy because of all the hard work you've been doing so far this semester. I'll see you in lab. Remember, it's the first half of the alphabet at 3, the second half of the alphabet at 2, right? That's what we talked about earlier? All right, so I'll see you this afternoon.